the United States Navy aircraft carrier USS Yorktown. CV-5 entered the most decisive engagement of the Pacific War on entirely borrowed time. Just days prior to the engagement, shipyard crews at Pearl Harbor had to pull off a brutal, compressed repair sprint, measured in a matter of days, to patch severe combat damage sustained in a previous battle. The engineering teams had no time to return the ship to full, yard-perfect strength. Instead, they completed temporary repairs judged sufficient for immediate operations and sent the carrier straight back into the hostile ocean. This massive constraint defined her final mission. She sailed into the Battle of Midway with no room to absorb another hit. On June 4, 1942, an overwhelming aerial assault intercepted the carrier. Enemy dive bombers broke through first and scored 3 bomb hits. Later, torpedo planes coordinated a follow-on strike and landed 2 aerial torpedoes. The underwater explosions tore open plating along her port side below the waterline. With flooding spreading and vital systems disrupted, power and propulsion were lost, leaving the massive vessel dead in the water. These dual torpedo impacts immediately triggered a catastrophic and highly complex chain reaction known as progressive asymmetric flooding. A warship is essentially a vast grid of watertight steel boxes. When explosions and shock damage compromised boundaries, piping, fittings, and watertight closures on the port side, the ocean rushed into outer voids, fuel tanks, and lower machinery spaces on only one side of the center line. This sudden influx of thousands of tons of uneven water weight shifted the ship's balance. As port compartments filled, the list deepened and water progressively spread through damaged connections and imperfectly sealed internal openings into adjacent spaces. This unchecked progression pulled the carrier further and further off its vertical axis. The resulting geometry was a severe and immediate list to port that reached about 23 degrees. At more than 20 degrees, the ship's stability margin shrinks fast. The massive flight deck pitched so violently that basic navigation on foot became almost impossible. The center of gravity shifted dangerously close to the point of no return, and the carrier threatened to capsize entirely. The initial damage assessment dictated that structural survival was mathematically highly unlikely. This prompted a logical command decision to abandon the heavily listing ship. However, the shattered vessel refused to flip over. The rugged internal subdivision of the hull managed to trap just enough atmospheric volume to maintain a fragile reserve buoyancy. This trapped air kept the ruined flight deck barely suspended above the waves. Recognizing that the heavy hull had stabilized enough to remain afloat, ships alongside began rigging towing arrangements, and a slow tow got underway. A volunteer salvage party then reboarded on June 6th, returning to a heavily listing vessel with no power. Their technical objective was to restore as much control as possible, pumping out flooded spaces where they could and using controlled counter-flooding to reduce the list. They needed only enough stability to keep the tow moving and bring the wounded carrier toward safety. The salvage crew managed to pump out several internal compartments and slowly began righting the massive hull. But the delicate operation was violently interrupted. An enemy submarine successfully penetrated the defensive perimeter and fired a spread of 4 torpedoes directly into the salvage zone. One struck the destroyer USS Hammond alongside the carrier. Almost immediately after, 2 more torpedoes hit Yorktown amidships on her starboard side. The attack shattered the fragile progress the salvage team had spent hours securing. The internal flooding accelerated far beyond any mechanical pumping capacity. Stability margins collapsed as water raced through the ship, and the carrier's fate was sealed. The salvage crew was forced to evacuate the vessel permanently. Under the massive accumulated water weight, the port side went under completely. The immense steel Leviathan finally rolled over and sank at 0701 on the morning of June 7, 1942. The heavily damaged carrier slipped beneath the surface, initiating a long free fall into an unknown abyss that would hide her for over half a century. 16,650 feet, roughly 3 miles below the surface of the Pacific Ocean, lies a radically hostile physical environment. Down there, darkness is total, and hydrostatic pressure is the defining threat. The ruined hull of the massive aircraft carrier plunged into that abyss. To understand the resting state of the vessel requires understanding the lethal physics of the deep seabed. At that depth, the water temperature hovers just a fraction of a degree above freezing. The sheer column of ocean water pressing down on the steel plates exerts over 7,000 pounds of force per square inch. This magnitude of pressure violently compresses any trapped gases, and any sealed voids can collapse until flooding and pressure equalize. Human survival is physically impossible here, and even advanced mechanical systems face severe structural limitations. When the enormous mass of the ship finally slammed into the flat, abyssal plain, the asymmetric water weight that had originally pulled her under settled permanently into the deep mud. The surrounding environment immediately began acting on the shattered steel, but not in the way traditional salvage models predict. In shallow sunlit waters, a sunken vessel is rapidly consumed by the local marine ecosystem. Oxygen, sunlight, and warm currents create a highly active habitat for coral, sponges, and aggressive wood-boring organisms. Shallow wrecks literally dissolve over mere decades as the biological load eats the ship alive, while tidal surges tear apart the weakened superstructure. However, that descent completely changed the equation for the ruined carrier. In the abyss, there is no sunlight, and cold temperatures can slow many chemical and biological processes. Oxygen levels and currents still vary, shaping how fast corrosion proceeds and what can live on the wreck. It is not a zero zone, but a quieter deep-sea regime where decay often looks different, and sometimes slower, than it does in sunlit coastal seas. Because the carrier sank into a cold, lightless deep-sea environment, many familiar drivers of shallow water wreck decay do change. Some organisms that attack wrecks in warmer, sunlit seas are less dominant here, and lower temperatures can slow certain reactions. But life still colonizes hard surfaces, and corrosion still continues, just under different conditions and at different rates. The crushing depth remains the great barrier to physical recovery, but it does not guarantee absolute preservation. Any engineering or survey effort to interact with the resting site faces a monolithic physical barrier. The roughly 3-mile column of seawater rules out conventional human diving, forcing a purely remote, robotic approach to the site. The environment is entirely unforgiving to traditional marine salvage methods, rendering cables, pontoons, and manned cutting equipment completely useless. To even look upon the wreck requires highly specialized survey technology, designed specifically to defeat the immense pressure and the freezing temperatures. The abyss guards its contents with an ironclad physical law that separates the wreck from the surface world forever. Deep water can slow some forms of decay, but it does not guarantee absolute preservation. But before visual confirmation of the wreck's condition could be achieved, survey teams had to find a way to map a target completely enveloped in freezing black water. Optical sensors are completely blind at a range of more than a few dozen feet in the deep ocean, making visual searches for a sunken hull mathematically impossible. To locate an object hidden under 3 miles of total darkness, marine engineers must abandon light and rely entirely on sound. In May 1998, a deep ocean expedition led by Dr. Robert Ballard arrived at the estimated loss coordinates. The team faced a staggering search grid covering hundreds of square miles of flat, abyssal plain. Dropping a tethered camera blindly into this massive area is equivalent to searching a dark continent with a single flashlight. The probability of intersection is statistically zero. Instead, the survey operation deployed a highly specialized towed array to execute a wide-area acoustic search. The surface vessel dragged the sensor package back and forth across the target zone in tightly controlled parallel tracks. This methodical grid pattern relies on the specific physics of acoustic swath mapping. The towed sonar vehicle continuously fires high-frequency sound pulses outward and downward through the freezing water column. When these acoustic waves strike the featureless, muddy bottom of the ocean floor, they absorb heavily and return a weak, scattered echo. However, when the sound energy hits a hard, angular, metallic structure, the dense steel reflects the ping back to the receiver with massive intensity. The sonar system measures the exact time it takes for the sound wave to travel down, bounce off a target, and return. Because sound speed through seawater can be modeled and corrected for changing temperature, salinity, and depth, the computer translates these returning echoes into precise distance measurements. The digital processing hardware on the surface ship constantly aggregates millions of these individual distance measurements. As the array continuously sweeps the designated search zone, it paints a highly detailed topographical map using invisible sound instead of optical light. A massive warship resting on a flat seabed creates a distinct disruption in the acoustic returns. The hard steel generates a bright, high-intensity reflection on the monitor. Immediately behind this bright return, the physical mass of the hull blocks the sound waves entirely, casting a long, dark acoustic shadow anomaly across the digital map. The sharp, mechanical right angles of a man-made weapon of war cannot be replicated by natural geology. The length, width, and overall geometry of this shadow tell the survey engineering team the exact height and length of the object projecting above the flat mudline. Maintaining the precise geometry of this acoustic net requires absolute control over the towing vessel. At a depth of 3 miles, the heavy armored cable connecting the surface ship to the sonar sled acts as a massive drag weight. A single course correction at the surface takes hours to translate down the entire length of the miles-long tether. The ship must maintain a creeping speed of just 1 or 2 knots to keep the sonar array flying at the correct altitude above the bottom. If the sled drops too low, it risks slamming into unseen geological ridges. If it flies too high, the acoustic pulses spread too thin, degrading the resolution of the returning map and potentially missing the target entirely. For several days, the 1998 expedition held its grid with relentless discipline, searching for the specific geometry of an aircraft carrier. Their persistence was rewarded when a long, distinct shadow anomaly materialized on the digital readout. The high-intensity return, paired with its dark acoustic wake, matched the dimensional profile of a major fleet unit, steel geometry no natural seabed could mimic. The target coordinates were strictly locked, ending a 56-year search. An acoustic shadow proved a massive steel object rested on the bottom, but sonar alone could not confirm the structural state of the shattered carrier. Entering the shattered interior of a sunken warship with a remotely operated vehicle is a game of high-stakes geometry. The jagged and collapsed bulkheads of the ruined flight deck create a lethal mechanical trap for any tethered system. The deep ocean currents constantly push against the equipment, threatening to force the fragile optical cables into sharp, torn metal edges. Following the discovery of the massive acoustic shadow anomaly, modern survey teams transitioned to the next phase of the mission. They deployed sophisticated robotic camera platforms to achieve precise visual confirmation of the wreckage. Descending out of the black water, the powerful halogen lights illuminated an impossible sight. The immense aircraft carrier sits largely upright on the massive abyssal plain. Some of her heavy anti-aircraft guns remain angled skyward, frozen as they were left in the chaos of her final battle. The ship is not reduced to a featureless scatter of scrap, but remains remarkably intact in major sections. Up close, only a remotely operated vehicle can perform this kind of visual forensics. The command team on the surface vessel drives a multi-million-dollar titanium robot situated 3 miles below them. The pilot operates the machine through a tethered optical feed, an umbilical cable composed of specialized power lines and fiber optic glass. This critical tether transmits high-definition video and instantaneous telemetry up to the surface, while simultaneously sending precise, real-time thruster commands down to the vehicle. However, this lifeline is inherently the greatest operational vulnerability of the entire system. Managing the slack of a 3-mile cable is an exercise in strict mechanical discipline. If the tether loops around a piece of jagged deck plating, or if the deep ocean current pushes the line into a shattered elevator shaft, the robotic vehicle becomes permanently snagged. Reversing out of a complex interior space requires absolute pilot situational awareness. The pilot must manage the thruster wash carefully, as firing vertical propellers inside an enclosed bay immediately stirs up thick clouds of deep sea silt, instantly dropping the visibility to 0 and blinding the optical sensors. Navigating the exterior of the upright hull provided a critical visual baseline, but the true engineering test of this telepresence system occurred during deliberate internal penetrations. During a highly specialized expedition in 2025, the deep water pilots guided their primary camera vehicle through the massive openings of the aft hangar deck. Inch by inch, they worked the line through twisted bulkheads and collapsed elevator platforms, keeping it clear of every jagged edge. Once safely inside the massive enclosed aviation bay, the high-intensity lighting swept across the perfectly preserved deck plates. Deep within the submerged cavern, the visual feed relayed an entirely unexpected artifact. Parked inside the aft hangar space was an automobile, tentatively identified as a 1941 Ford Super Deluxe Woody, with ship service markings that suggest it served the ship rather than a private owner. its silhouette and key features still read clearly in the camera lights, preserved enough to raise a new set of questions about why it remained aboard. The robotic cameras documented every angle of the machine, using minute thruster inputs to hover just inches away without making contact. The pilots executed a highly controlled grid pattern within the hangar, capturing thousands of overlapping high-resolution images to digitally reconstruct the interior space. The footage suggested remarkable preservation in many sections, but every discovery and maneuver remained governed by a single rule: nothing comes off the wreck. Every deep water marine operation faces a fundamental choice between physical recovery and absolute preservation. For this vessel, that choice was made in 1942. When the volunteer salvage team boarded to pump and counter flood, they were still fighting for buoyancy when the enemy submarine broke through. 2 torpedoes ended any realistic hope of saving the ship, and the sinking that followed turned Yorktown into a final resting place. One reason the site is treated with extraordinary care: because this massive steel structure serves as the final resting place for these sailors, the wreck site triggered an irrevocable legal and moral boundary. Under international practice and United States law, a sunken military vessel is generally protected by sovereign immunity, and wrecks like this remain the property of the United States government as protected sunken military craft. That status blocks commercial salvage claims and prohibits disturbance or removal without explicit authorization. This strict protocol dictates a look but do not touch approach to all expeditionary operations. Remote vehicles must hold carefully calculated standoff distances, and success is measured in non-destructive data, not in steel brought to the surface. Even the most compelling artifacts remain in place. The expedition is restricted to mapping the exterior geometry and internal spaces with harmless light and advanced sensors. To enforce this rigid legal boundary, modern survey teams operate under extreme procedural discipline and constant institutional oversight. Before a robotic vehicle ever enters the water, the dive plan is meticulously reviewed by naval historians and marine archaeologists to ensure absolute compliance. During the dive, every thruster movement is mathematically calculated to prevent even the hydraulic wash of the small propellers from disturbing the fine silt that has settled across the massive flight deck. The legal wall built around the shattered wreckage is further reinforced by the overwhelming physical barrier of the ocean itself. While commercial marine salvage operations in shallow coastal waters frequently battle illegal looters and unauthorized divers, the immense depth of this specific site serves as an impenetrable vault. No unauthorized vessel possesses the complex technological infrastructure required to lower heavy grabbing equipment 3 miles down into the freezing darkness. The legal protections established by the Navy and the crushing physical environment work together in absolute synergy to defend the resting site. The strict non-invasive mandate guarantees that the final moments of the fallen salvage crew are never violated by industrial cutting torches or mechanical recovery claws. The scientific survey teams willingly accepted this trade-off knife, choosing to construct a highly precise digital replica of the carrier rather than tearing the historical ship apart for museum pieces. The mission parameters demand that the true physical evidence remains securely locked on the abyssal plane. Protected by law and extreme pressure, the carrier is frozen as a permanent monument accessible only through data. For more than 8 decades, the massive warship remained completely isolated in total darkness, sealed away from any human intervention by an insurmountable column of water. Then modern deep ocean survey windows finally pinned down her resting state. At 16,650 feet, the carrier sits upright on the flat abyssal plain, with major sections still reading as a warship, not a scrap field. Heavy anti-aircraft batteries remain angled skyward, frozen in their final combat orientation, geometry held in place by the environment itself. Because crushing pressure and near-freezing temperatures reshape the deep-sea equation, many shallow water wreck killers are less dominant here, even as corrosion and colonization continue on their own timetable. That helps explain why the hull can still present as a stable, upright monolith instead of a collapsed debris field. But the same depth that preserves these lines also enforces the rule of the site: look, document, and leave everything in place. The overarching goal of the modern mission was never to recover physical pieces of the hull, but to map its current state without inflicting structural disturbance. To achieve this objective, marine survey engineering teams transitioned from simple visual observation to advanced digital photogrammetry. Pilots flew sophisticated remote camera platforms along the carrier in hundreds of methodical, overlapping passes, bathing key surfaces in high-intensity light while holding strict standoff distances. Surface computers then matched reference points across armor and superstructure and stitched the imagery into a mathematically precise three-dimensional model of the wreck site. The result is a comprehensive digital twin that effectively drains the ocean away within a virtual environment, letting historians and engineers inspect battle damage and geometry in clear detail. Establishing this high-resolution digital baseline serves a dual purpose for the future of the resting site. First, it sharply reduces the scientific pressure for any future physical intrusion by delivering broad, detailed access in a virtual space. Second, the dimensional map places the carrier on a long-term preservation watch list. If subtle environmental shifts or slow structural changes occur over the next century, future remote surveys can compare new data against this baseline to track how the wreck is evolving over time. The operation proves that marine engineering can successfully penetrate the most hostile environments on the planet to gather absolute structural proof without violating the sanctity of the site. The staggering depth of 16,650 feet continues to provide an impenetrable physical vault, while the digital data ensures the historical and technical truth of the vessel is fully secured for future generations. The massive aircraft carrier remains completely undisturbed on the dark ocean floor, existing exactly as she did when the last survivors abandoned her to the deep. The high-resolution baseline guarantees the ship is never lost again, completing the mission without ever breaking the surface.